Okay, so on the continuing topic of oscillations, first of all, just a conceptual exercise in graphing. So let's imagine that we have a mass and it's in harmonic motion, and then it's left, and we'll just use the usual coordinate system where right's positive. So that means it's on the negative side, and it's moving to the right. So that's the direction of its velocity, and its position is negative. And we want to sketch position and velocity graphs. Well, first of all, we visualize what's going to happen next, right? So the mass here is going to start on the negative side, then it's going to go through 0. It's going to go up here to positive A, and turn around and go back to negative A. So here we're starting, if this is the time axis, time, and this is position, our initial position value is negative, but it's not as much as negative A. We're not that far away. And from that initial location of negative, we go up to a 0 position. That's right here. And then we go up to positive A, and then back to 0 before we go down to negative A. Now, it's important visually that it be really clear that the initial position is not at negative A, and this graph clearly shows that. Now, really all you need to do is just take this red line and just rotate it sideways, and then you'll get essentially this graph. So really just look at this sideways. You'll see it's negative, it goes up to 0, then positive A, negative A, and so on. Okay, so that's the graph of position versus time. We also want to make a graph of velocity versus time. Now, there's a couple of ways to do that. You can use the techniques of calculus and just differentiate this graph, because we know that velocity is the derivative or the slope of the position graph. So here you see a positive slope, a positive maximum slope, a 0 slope, a negative maximum slope, and a 0 slope. So you could simply graph slope down here, and that would work fine. Alternatively, you could think about the velocity and its changes. So right now we're starting with a velocity that's positive. Yes, no surprise, it's a positive slope here too. But it's not its maximum. The maximum speed is going to happen next, up here at 0. So that means the velocity here is going to go up. So it's a maximum positive velocity. Over here, it's still moving to the right, but the velocity, the speed is getting slower. So we still have positive, but getting slower, and then here at the end it stops. So at this point here, up at maximum position, our velocity has dropped down to 0. Then the velocity starts off to the left and slow, that's negative. And then right here, back at the equilibrium point, we're now going left at maximum speed. And then, still moving to the left, we slow down to stop. So it looks like that. So as we said, like if you consider the slope, here it's a 0 slope, that corresponds to 0 velocity. Here it's a negative maximum slope, that corresponds to negative maximum velocity. Here, the slope of position, the velocity is 0. Here, the slope of the position, whoops, the slope right here, sorry. That's a terrible slope. Here our slope is, again, a positive maximum, as per this graph. Okay, so that's a little graphing exercise. Next, something mathematical. Now, we considered in our previous classes, our previous oscillation problems, just masses that started off at plus A, at minus A, at 0 moving left, and at 0 moving right in the positive direction. But really, it could start off at an in-between state. And we will then have to solve this equation, use the initial condition. So what is the position at time 0 in order to find what the initial phase angle is? It's not going to be one of these nice ordinal points. Here's an example. So here we've got a mass moving to the right, and it's 40 centimeters from equilibrium. So we're not starting at maximum speed in equilibrium, and we're not starting out here at plus A, because the mass is going to be moving for a little while anyway to the right to reach that stopping point where it turns around and goes back and forth and back and forth and back and forth. So out here, this is plus A. In here, this is minus A. So you see we're in an in-between state, and we want to describe this, this motion mathematically. We want to come up with an equation with position as a function of time. So first, let's find the amplitude. there's three variables we need to describe the simple harmonic motion: amplitude, rate of vibration, and initial phase. So for the amplitude, we want to find the distance, maximum distance from equilibrium. Well, way out here, it's actually going to stop. So we can use an energy equation to figure out how far it goes before it stops. So the energy at the beginning, this picture right here, it's moving, so we have kinetic energy. And the spring is stretched 40 centimeters from equilibrium, so we have spring energy. There's no friction or dissipation, so no non-conservative work. And then at the end, when it stops, there's no kinetic energy, there's just spring energy. So we've got 1/2 mv initial squared plus 1/2 kx initial squared equals 1/2 k, and we're going to call the final stretch of the spring this amplitude A. So the mass is given, the initial speed is given, the elastic constant is 32. We put in 0.4 for the initial stretch. And then we can solve this equation for the amplitude. Solving, we get 64 centimeters, 0.64 meters. So it's going to go about another 24 centimeters before stopping. Okay, so that was familiar energy conservation calculation. The next thing we need is the rate of vibration omega. Now that's given by the root of k over m. So it varies with the root of the elastic constant, that's 32, and inversely with the mass, the root of the mass. So that's root 16, which is 4 rads of oscillation for every second. Now the next thing we need is the starting point, the initial phase of the vibration. Now here we're going to have to do a little trigonometry. The initial phase, the letter is delta. That's horrible handwriting. That says rate of vibration. There, I don't know if that's any better. Okay, so for the initial phase, we'll put in what we know already. X is, well, here's standard form, a cosine omega t plus delta. Now we know the amplitude is 0.64, and we know omega is 4. But we'll put in the fact that at time 0, the position is plus 0.4. And we'll substitute all that in here. So the amplitude we know is 0.64. Omega we know is 4. We're going to put in time 0 and the position of 0.4. Put in those initial values for x and t. And now we have an equation that we can solve for delta. So we divide both sides now by 0.64. And we see the cos delta is 0.4 over 0.64. So delta then is the inverse cosine of 0.4 over 0.64. So let's see what that is. So 0.4 divide 0.64. And then we'll do second, make sure we're in radians mode, second inverse cosine. Okay, it's 0.895, it's about 0.90 radians. Now, we're not quite done because we need to consider quadrant. Okay, we need to consider, ultimately what this is about is the direction of the velocity. Because we're moving right, this means that we're going to need to pick the correct value for the initial phase because the initial velocity is positive. You see, we know that for a cosine being positive, as this side of the equation is, that we could have a solution in quadrant 1 or a solution in quadrant 4. Right? Cosine is positive in both of those quadrants. So which one should we pick? Well, if we look at the motion, then we see that for our graph, right, that we're going to move to plus a. So we're starting on the positive side, and we're going to move towards plus a. So if we were to sketch that, you would see that we have this graph here. And then and so on and so on and so on. So this is the point at which we're starting. Now, if we compare that with an unshifted cosine, okay, so this is a graph of cosine, we see that we're actually starting this example over here in quadrant 4. Now the 0.895 or the 0.9 radians is the quadrant 1 answer. That would correspond to a velocity that's negative, moving to the left, a negative slope. But our velocity is over here, positive. So we need actually the quadrant 4 solution. So comparing an unshifted cosine with the actual graph in this case leads us to the conclusion that we need a quadrant 4 solution. And therefore, that the actual delta is 2 pi minus 0.9 radians, which is 6.28 minus 0.9, so that should be about 5.38 rads. So if we put that all together, we get the following equation to describe this oscillation. And that was the task. Now, having done that, and here's the answer right here, we can now, given position, find the time. So let's find out how long it takes to get here to the end. Now, we're going to get to the end repeatedly. There's going to be lots of times when we're here, but it says what's the first time that we get there. Okay, so when x is positive 0.64, what is the time? So we can substitute that in for x, and then there's only going to be one unknown in this equation. Now I had 5.38 on the previous page. Here I have 5.39. That's just a bit of round off error, I guess. So we're going to divide both sides by 0.64. We'll get 1. At this stage we want to solve for t, so we're going to do the inverse cosine of both sides. Now the inverse cosine of 1 is an angle. We'll talk about that in a second. We can see, though, that to solve for t, we're going to take this angle, the inverse cosine of 1, we're going to subtract 5.39, and we're going to divide by 4. And this will be the value of t. Now, what is the inverse cosine of 1? Which angles have a cosine of 1? Well, this is going to be the inverse cosine of 1. That's going to be 0, 2 pi, 4 pi, etc., i.e. it's 2 pi times some integer, like n. So I put in 2 pi n minus 5.39, and I divide by 4. So that is all times at which the mass will be out here at the end. Now putting in n equals 0 gives you a negative answer, which doesn't make any sense. So we put in n equals 1, that's the first one that works, so we get 2 pi minus 5.39, that's 0.9, divided by 4, that's about 0.25 seconds. So that'll be the first one. That's for the n equals 1 solution, but then of course there'll be others, n equals 2, and so on and so on. Now I said this was intense mathematics, and indeed it is. It's not a whole lot of fun, but it really is just an application of solving trig equations. So now, one here for you to try. Okay, so draw a diagram, find the equation as a position of function of time, so find the amplitude, rate of vibration, and initial phase, and then use that to find the times when the mass is at the lowest point. So you can pause the video right here, give it a try on your own, and then play the video to watch my solution. Okay, so hopefully your solution looked like this. So here we've got a spring from the ceiling, and then we hang a 7.5 kilogram mass from it, and it reaches equilibrium. And then we pull it down and let it go. And so here's the release point right here. So it's released here from rest. At some later time, it's below equilibrium, 20 centimeters or 0.2 meters below equilibrium, and it's moving down at 0.65 meters per second. So we'll use the coordinate system where we measure distances from equilibrium. So this is x prime at the end, and this is v. Here, the x prime is going to be the amplitude. Amplitude is the maximum distance from equilibrium. So an energy equation, energy at release plus gains or losses equals energy at the end. An energy equation can be used to find the amplitude, because here at the release point there's no kinetic energy, there's just prime spring energy. Here at the end you have both prime spring energy and kinetic energy, and this is a conservative system. So there's no gains or losses of energy. So this is 1/2, now what was the K value again? 200. So to give you a vertigo there. This is the unknown amplitude. On this side we've got 1/2 of 200 times our 0.2 distance from equilibrium, and then this is 1/2 times the mass times 0.65 squared. That would be the kinetic energy. Now what was the mass? 7.5 kilograms. Okay, so we solve this equation for the amplitude, and we find that the amplitude is 23.6 or 23.6 centimeters or 0.236 meters. Next, you find the rate of vibration. It's the root of K over M. So it's 200 over 7.5. And so what does that work out to? Okay, that should work out to 5.2 after you take the square root. Okay, so both of those are pretty standard calculations. Now we get to the slightly harder point. Now for the initial phase, delta, if we look at the graph of the motion, we see that we are below the equilibrium point, we're negative, and we're going down. So I guess I could just do it up here. Better. So we're here, right? And we're going to go down to negative A and then come back up like that, and so on and so on and so on. So that graph, and I'll just repeat it down here, if you compare that with an unshifted cosine, so this is the actual motion, what would an unshifted cosine look like? So cosine just goes like this, right? So we see that our actual motion is starting here, and that's in quadrant 2. So we want an initial phase angle that's in quadrant 2, because we're starting the motion here negative and going down to negative A, and that corresponds to quadrant 2. So we expect delta to be in quadrant 2. So let's set up what we know so far. So we know x is 0.236 cosine 5.2t plus delta. Then at time 0, the position was below equilibrium, 0.2. So we put those in here. Okay, putting in 0 for t just wipes out this whole term, and you get cosine or delta. So we divide both sides by 0.236. And then we do the inverse cosine of both sides. Now, because we're doing the inverse cosine of a negative number, the calculator will automatically give us a value in quadrant 2. 0.2 divided by 0.236 equals, okay, make it negative, and then do the inverse cosine. So 2.58 rads, and if you check, you'll see that is actually in quadrant 2. So now we've got the equation for height or position as a function of time. It's 0.236 cosine 5.2t plus 2.58 radians. And that's what we were asked to show. Right there, we've done it. Boom. Now, to find the times at which the mass is at its lowest point. Well, at the lowest point, that implies h is minus 0.236. So you put minus 0.236 on this side. And you try and solve for t. So dividing by 0.236 just gives you minus 1. Oops, 5.2t plus 2.58. So we're going to do the inverse cos of both sides. So we need to do the inverse cosine of negative 1. And, oh my goodness, this should be 2.58 if I write neatly. And now to solve this for time, so we're going to bring this over and divide by 5.2. And we were asked to find all the times, so this is an expression for all of them, but we still need to say which angle has an inverse cosine of negative 1. Or sorry, yes, which angle What is the inverse cosine of -1? Well, this is pi. Pi has a cosine of -1, but so does 3 pi, so does 5 pi. This is odd pi's. Now in math, the formula for an odd number is 2n plus 1 pi's minus 2.58 over 5.2. That's a formula for all the times, putting in n equals 0, 1, 2, 3, 4, 5, all the times at which the mass reaches the bottom. Now that's a lot to chew on, but you have the video and you can replay it a couple of times just to try and get the idea. And we'll work on one like this together in class.